Hi, I'm Lene Fiora. My partner is Sarah Dickey, and our project is called Mood Waves. Our product is an electroencephalogram, or EEG, that will use brain signal output to better understand patient emotions. Each emotion detected in the EEG signal will correlate to a specific programmed LED that will light up depending on the signal detected. Our product would be particularly helpful when treating nonverbal autistic patients. Autism spectrum disorder is an umbrella term used to identify a variety of neurodevelopmental disorders. These disorders are grouped together because of how they interfere with a person's ability to communicate, socialize, behave, and develop. Autism patients will have some difficulties or delays with communication and speech, and because of these difficulties, it often leaves parents and healthcare workers in a tough situation when trying to communicate with these patients, and knowing their emotional state would be beneficial to their care.
Another potential application would be for people suffering from traumatic brain injuries. The CDC classifies a traumatic brain injury as a disruption in the normal function of the brain that can be caused by a bump, blow, or jolt to the head, or any penetrating head injury. Many times, these head injuries actually do result in a complete or partial loss of verbal communication capabilities. In addition, there's also an umbrella term called aphasia that could also benefit from our product. These conditions are classified under the general term, which is a disorder that results from damage to the areas of the brain that produce and process language. Aphasia results from damage to one or more of the areas of the brain responsible for language. Aphasia can occur suddenly, such as after a stroke, or may develop more slowly as the result of a brain tumor, infection, or neurological disorders such as dementia or Alzheimer's.
Regardless of the cause, loss of verbal communication can be frustrating for both patients and caretakers. Treating nonverbal patients often results in loss of hours for healthcare workers, which in turn means lost money and wages for hospitals and healthcare facilities. In a private setting, caretakers of these patients may have difficulty understanding what the patient is trying to communicate. This can inhibit the ability to understand a patient's needs, from pain and food needs to simple things like their favorite activities. Our product's simple and cost-effective design can help change the way we interact with these patients. Our design will allow professional and private healthcare workers to simply apply several electrode pads to a patient to get a quick readout of their emotional desires or well-being. We're hoping this product may be able to help these caretakers get answers to the questions that are so often needed but hard to communicate for the patients. Simply ask the patient a question, and an LED light will light up indicating the patient's emotional response.
We believe that our product is unique, cost-effective, and easy. As of today, there are limited options established for a brain-computer interface made as a communication tool for nonverbal patients. As we discussed earlier, face-to-face communication enables access to emotional information that these nonverbal patients may not be able to express their emotions or communicate their negative feelings. The few machines that are currently on the market that could potentially accomplish such a task are currently being sold for upwards of $2,000 and are not configured to register emotions in a simple output. Additionally, these expensive machines are not readily available to the private market or for in-home use. Our product is designed to be cost-effective at an estimated $60 per unit, and we would like to eventually add Bluetooth capability to make our product even easier for private in-home use. There are several examples of companies that may be interested in our product, as you can see here. And according to the Grandview research, the market worth for EEG systems and devices is projected to reach $1.6 billion by 2026, meaning our product would fit right into a highly profitable market.
An EEG is a test used to evaluate the electrical activity in the brain. Brain cells communicate with each other through electrical impulses, so an EEG detects potential problems or signals associated with this activity. Put simply, an EEG tracks and records brainwave patterns. The signals shown on the left are examples of different waves that are correlated with several mental states. Our goal was to measure alpha and beta waves and distinguish between the two. Alpha waves occur at 8 to 12 Hz and are associated with a state of rest. Beta waves occur at 12 to 30 Hz and are associated with a state of concentration. After doing some research, we found that it would be most advantageous to measure these waves from the frontal lobe, as it is the part of the brain that controls cognitive skills, including emotional expression and language. We also found that the concentration of each wave could tell us more specific things about thought patterns depending on where we measured them from. For example, alpha concentrations on the left motor cortex increase when you think about using your right hand.
Initially, when we were designing our product, we used several DIY tutorials on the Instructables website. We used 2 different sites on building an EEG and one for programming the signal to correlate to specific LEDs on a breadboard. We did use minimal parts, however, it didn't mean that it was any easier. Some of the parts that we used were simple, like capacitors, resistors, shields, filters, electrode leads and pads, and several wires. We needed to obtain the signal from the brain while also reducing the noise from the circuit enough to get a good signal into our computer where we would be processing the data. In order to do this, it required a lot of filtering and dampening of the signal. We noticed when we were doing our research that there's actually about a 7 hertz voltage across the forehead on the skin itself. So we used a 7 hertz high pass filter to actually dampen the voltage. We used 2 60 hertz notch filters to filter out the noise from the wires on our circuit board itself. We used an instrumentation amplifier to actually amplify the reading coming from the EEG leads. And a 31 hertz low pass filter was used to filter the actual brain waves themselves and get rid of extra noise that was above the alpha and beta waves that we were looking to measure. Even after all these filters were applied to the circuit, we had to do some troubleshooting. We noticed that there was still too much noise in our circuit. To troubleshoot that, we actually added in another 60 hertz notch filter to account for all the noise from the circuit board.
To collect our data, we used basic electrode leads, which are shown here on the right, that were purchased from DigiKey. These were connected to electrode pads to collect the brain signals. The electrodes were placed in positions F7, F8, and FP1, shown in the figure on the left, or the right, excuse me. We then connected the leads to a 3.5 millimeter audio jack and into our computer using a pre-written program that we were able to find on Instructables. Once we were able to obtain a signal, we attempted to correlate these signals to specific emotions. Unfortunately, due to budget limitations, we were only able to purchase 3 electrode leads, which proved to be insufficient for what we were trying to accomplish. We were able to obtain and view signals in the brain, however, they weren't sufficient to distinguish between emotions.
Because of all these budget limitations, we decided to compromise. We were limited on time, budget, and supplies, so we decided to move forward and at least get 2 dependent LED lights to light up. We wrote a program that would correlate a calm state to a blue light and an excited state to a yellow light. Although we were successful in this, the lights weren't especially useful as they weren't correlated to specific emotions. It is our belief that with more time and resources that we would have been completely successful with our project. We found that with more EEG leads would be required. We found that more EEG leads would be required to fully accomplish our project, but with more EEG leads, we would need to put more filters into our project as well. Because of the COVID-19 pandemic, shipping times are unusually slow and would not be conducive to finishing this project on time. Both myself and Lene are planning to continue our research throughout the summer to fully design and manufacture this product.
Here you can see the signal being collected from our circuit, and here is the circuit itself. And as you can see, the signal is flashing between the yellow and blue lights because the leads were not sufficient enough to collect the correct signal. Here you can see the electrodes on my face to collect the signal, and that was our circuit operating.
And on this final page, this just shows some of the sources that we use to kind of collect all this data and make this project work. Thank you very much for watching.
Thank you.